everyone. How are we doing tonight? All right, who's excited for tonight's lecture? Okay, we love that. Well, welcome to Big Brain. Thank you guys so much for being here tonight. My name is Rihanna, and I'm going to be your host for tonight. Thank you. I'm not like the singer, I'm sorry, I can't sing like her, but I want to first give a huge shout out to our venue, the University Art Bar, for hosting us tonight. Feel free to grab a drink throughout the lecture, support the space, and show them some love. But with that being said, I'm excited to introduce tonight's speaker, Dr. Akshatha Vydula, a postdoctoral researcher at the University of Richmond studying observational cosmology. She works with radio telescopes worldwide, including EDGES and NASA's upcoming LuSEE-Night lunar mission. Please give her a big welcome.
Hey everyone. First of all, thank you so much for taking the time out on a weeknight and coming out here. I'm very excited to see all this crowd here. Very excited to hopefully give you something to take back home today. But before we get started, just by show of hands, I just want to take a quick poll. How many of you on the way here listen to radio? I'm talking good old FM radio. Okay. How many of you are old enough to remember what an FM radio is? Okay, there we go. That's more like it. Okay, so today we're going to learn about what these radio telescopes can do, and especially in understanding the origin and evolution of the universe. I'm going to give a quick overview of who I am. I grew up in a small town in Karnataka, in the state of Karnataka in India. And I went to high school there, moved to Bangalore, which is the capital city of Karnataka, and I did my undergrad in electrical engineering, moved to Netherlands, and I did a quick research thesis there for my undergrad at Kaptein Astronomical Institute, and I worked with a telescope called Low Frequency Array. It's one of the biggest radio telescope that Europe has. And then I moved to Arizona State, which is where I got my PhD in astrophysics. That's kind of also where I got involved in doing a lot of community outreach and giving talks like the one I'm doing today, getting involved with people around the city, getting them introduced to the science that we do, getting them excited about the science. Hopefully, hopefully I can do some of that today. And currently I'm a postdoc at University of Richmond in Virginia. Okay, thank you. Now let's do a brief cosmic history. Okay, universe as we now, how many PhDs does it take? Okay, hopefully just one. Okay, universe as we now know today began with Big Bang. And this animation here is a numerical simulation of neutral hydrogen. And why hydrogen? Because hydrogen is the most fundamental element in the universe, and it was the most abundant element as well in the early times of the universe. And so this animation actually uses the real initial conditions of the universe as we know now today. And in the beginning of the universe, there's nothing, right? There's just hydrogen gas. There's some of the regions are extremely overdense, some of the regions are underdense. And you can see in those overdense regions, the gravity starts acting. Those yellow dots that you see in the animation, those are stars. And those stars start coming together to form galaxies. And because these stars and galaxies are forming, it releases a lot of heat and radiation. And that sort of ionizes the neutral hydrogen around everywhere else in the universe. And so to be able to know what happened in the early universe, our observable is neutral hydrogen, because that's something that only existed in the early universe. Some of that does exist even today, but only in the inside of galaxies and around the disks of the galaxy. So our own Milky Way has some of that neutral hydrogen. So you can think of neutral hydrogen almost as if it's like a time capsule. It captures the information of the conditions at the time of the universe. And that's why we are after neutral hydrogen. Okay, I need to... Okay, there we go. And so this is a present-day universe. It's quite complex with a lot of structures around everywhere. This image is from the James Webb Space Telescope. You can see extremely dense, like clusters of stars and galaxies. And this wasn't always the case. Now, if we look at what happened before the first stars and galaxy formed, we have to ask ourselves, what is cosmic dawn, right? Dawn, as the word suggests, is when the light first appears in the sky. Cosmic dawn is when the light first appeared in the universe. Because before the formation of stars and galaxies, there was nothing. Everything was just dark, right? And so if we look at the timeline of the universe, this is a graphic showing, beginning from the Big Bang on your left, all the way to the present-day universe on the right. That cluster, let me see if this works. There we go, okay. This cluster that you see, sort of that blue and yellow hazy structure, that's the cosmic microwave background. We have experimental evidence of what that cosmic microwave background radiation looks like. So in a sense, we have experimental evidence of cosmic microwave background, which is a relic of Big Bang, and we can image the present-day universe. But everything in that red box is completely unknown to us. We don't know how the present-day universe is the way it is, and from where it came from. That's the reason why we are after neutral hydrogen. So if we look at in terms of discoveries, we have Nobel Prizes in making discoveries for the early universe. We have Nobel Prizes for what the universe looks like today, but there's an entire chunk of that region where there's just no data. So a lot of us that do this sort of cosmology observations, this is what we're after. So let's go back and look at that neutral hydrogen. Okay, this is gonna, bear with me here. So neutral hydrogen has one electron and one proton, right? So the electron has something called a spin state. And this, you have to go back to your quantum states of the electrons for this. But essentially, believe me, you just have to take my word for it. Okay, so the electron naturally wants to come to a lower energy state because that's more stable. And so when the spin state of the electron and proton are parallel to each other, that's a higher energy state than if we were to be anti-parallel. And so the electron sort of naturally comes to that lower energy state, and that leads to the emission of radiation with the rest wavelength of 1420 megahertz. But this happens very early on in the universe, right? But it happens in the beginning of the universe, in the very formative years of the universe. And so it gets Doppler shifted to about 50 to 200 megahertz. You can think of it as though it gets stretched by the time it gets released to the time it reaches our telescopes on Earth. So it's almost as if it's getting stretched through the space. And so that lets us sort of go back in time and do this sort of space archaeology of what the universe looks like. Okay, so for those of you in the audience, I know some of you did ham radio here before the talk. I talked to you guys. 1420 megahertz is actually protected for radio astronomy. So if you look at that yellow band there, that's protected by the National Telecommunication Information Administration. So for audience here who are into UHF radios, it is illegal to transmit anything at that frequency. Don't do it. But if that's all it was, I wouldn't have a job today, right? Because it's protected. Turns out, because of Doppler shift, it comes to 50 to 200 megahertz, which is reserved for TV and FM and satellite communication, air traffic control, and amateur radio communication, etc. Right? So if you were to be listening to FM radio, this is the frequency you would be dialing in. But we all want CarPlay now, so. So, okay, this is another, I guess, sciencey slide here. What I'm showing here is the 2D rendering of the 3D animation that I showed earlier. So on the x-axis, you have the age of the universe. So the leftmost part is the beginning of the universe, and the rightmost part is the present-day universe. And the bottom plot is the average across the y-axis. So we went from 3D to 2D to 1D. And for the observant audience, for the audience with big brains out there, you can see that the y-axis is measured in millikelvin, which is the unit for temperature. Now you might ask, why is this I did not do that. Okay. You might ask, why is this in millikelvin? The answer is cosmologists are weird, and we just like to see things as hot or cold. So this plot is plotted relative to the CMB temperature, the cosmic microwave background temperature. So what we are after is that little dip in temperature in a very particular age of the universe. So in that dip essentially lets us know the age of the universe and the evolution of the universe and how much stars, like how fast the stars were forming at the time, which we call star formation rate. And so essentially this is the song and dance of heating and cooling of the intergalactic medium at the time, in the early universe. So we are after that dip. So like I said, your car radio actually picks up the signal, even though it's so small. But that signal is only about 0.01% of the static. And by static, I mean, if you have two FM stations, and do you guys ever get frustrated that you can't find a channel between two transmissions? That static is, part of that static is actually coming from the early universe. So to get a sense of scale of what that looks like, this is like trying to listen to a hummingbird flap in the middle of a hurricane. This is like trying to listen to a whisper from the opposite side of a concert stadium in the middle of a performance. It is also like trying to listen to the finger snaps standing right next to the roaring jet engine. And I just want you to, kind of get a sense of scale of what that is and why it is so difficult to make this measurement. And since car radios are no good for us, we go out and build extremely sensitive radio telescopes. And if I say radio telescope, what comes to your mind? A big dish, a big communication disk. That's a lot of radio telescopes. I'm not gonna lie. This one right here on the left is from Very Large Array in New Mexico. So for those of you who remember the movie Contact featuring Jodie Foster, that movie was shot there. So, and then the one in the middle is Owens Valley Radio Observatory. It's right across from Mount Whitney in the Sierra Nevadas. And then the rightmost one, okay. I need to remember to not do that, okay. The rightmost one is called the Green Bank Telescope. This is the largest movable structure, and I have a video from my recent site visit there. You have to walk up through that catwalk, take the second elevator that's kind of leaning by about 30 degrees, and you go all the way up. And it is pulled by big tracks. I'll show you more cool pictures of that. But radio telescopes also come in different sizes and shapes. The one on the left is called the Edges. It's the size of a coffee table. The one in the middle is called the Square Kilometer Array. That looks like a Christmas tree. The one on the right is called Murchison Whitefield Array. That looks like a cluster of spiders. So we build all these extremely sensitive telescopes, but we do have a lot of observational challenges. One of them being our own Milky Way. Our own Milky Way, our backyard Milky Way, is extremely bright. It is about 1 million times brighter than the signal that we are after. We also have incomplete sky maps. And the reason why we have incomplete sky maps is because it turns out that in order to construct a full sky map, you need identical telescopes on both southern and northern hemisphere, because when you observe from the northern hemisphere, there's a region in the southern hemisphere that's not visible to us, and the same goes from the southern hemisphere as well. And so we haven't been able to do that so far. And we also have instrumental effects. By that, what I mean is the telescope itself adds certain characteristics to the data coming in. So here's an example of what that looks like. So on the left is an ideal telescope, and on the right is a realistic telescope. So telescope not only adds sort of these spatial features, so as this data is coming in, it kind of adds these structures in different parts of the sky as you're receiving it. It also adds the structures as you go from different frequency ranges. So that's what we call a spectral structure. So essentially, this is trying to, understand if it's a smudge or if it's a signal coming from the sky. So in order to do that, okay, someone got that. Okay, so in order to do that, we need to be able to understand the characteristics of the telescope itself. And finally, we have a lot of terrestrial radio frequency interference. This is a map of all of the FM stations that we have in the US, which I don't know, none of us are listening to them. So I guess I don't know why we have them. So. But anyway, so what we do is we go to very, very remote locations to avoid RFI. This is a current non-exhaustive list of the 21 centimeter signal, 21 centimeter experiments. We have some in the northern Canada region called MIST, Owens Valley, the one that I just showed you. We have a few in very remote deserts of South Africa. We have one in India and a few in the Australian outback. The crux of some of my research is this one called the EDGES, that is located in Western Australia. This is the experiment to detect the global epoch of reionization signal. This is a precision cosmology instrument that is specifically designed to study that signal coming in from cosmic dawn. And I mentioned that this is the size of a coffee table. So there's two of us sitting right next to it to sort of give you the sense of scale. This is located in the Australian outback. We are supported by the Murchison Radio Astronomy Observatory in Australia. And this is a satellite view of EDGES. Here you can see those sawtooth type structures. That's metal wire mesh, and we call them the ground plane. And we're going to get into the details of what that is. And the hut is a modified shipping container that contains that houses all of our electronics. We have conduits going from under the telescope itself, which is the center of that wire, the sawtooth structure, and it's wired to the hut. And we get our data downlinked, every night, and that's how we are able to do our data analysis. And even though this is mostly hands-off, we do have to go out there occasionally on yearly or two-year cadence to do maintenance and upgrades to our system. This is another aerial view of the base camp that we stay in the Australian outback. This is about 40 miles from where we deploy our telescope. It's quite Martian-like to live out there in Western Australia. It's mostly self-sustained, but we do get supply trucks once a week. This is the four-wheel drive that we have to drive there because there's just no roads. We also have a lot of safety devices, including something that we call a personal safety beacon that we are required to press every 30 minutes whenever we're driving to make sure that the ground, the base camp knows that we're safe. We also have a satellite communication device, but we were told that we should only use that in absolute emergencies. And if we do press that one button, they're going to send us the Australian Army. Thankfully, we didn't have to do it. This is another picture of the kitchen. Also a modified shipping container. This is the outside picture of the room that I stayed in, also a modified shipping container. You can see that everything is kind of raised above the ground. That is to make sure that the wildlife can roam around freely. So there's obviously like snakes and redbacks and whatnot. There's a lot of wildlife in Western Australia. These are iguanas. They're 6 to 8 feet long lizards. This one actually is a baby iguana that's hanging out right outside our entertainment center. There's kangaroos, emus, snakes, and poisonous spiders, which are all fun until they start chewing your wires, and then you're forced to take a trip to Australian desert. And so that's also one of the reasons why we like to go out there, fairly regularly to be able to do these maintenance. One of the things that we did on our most recent visit is what we call the ground plane survey. So this is sort of another point of view of that same sawtooth structure. It's about 50 meters by 50 meters in area. And it looks mostly flat, but it has these undulations of about roughly 15 to 20 centimeters, which is big enough for us to see those structures sort of affecting the quality of our data. So that forces astronomers and engineers alike to play civil engineer for a day and take measurements in the field. And especially when I was out there, it was the summer of Australian desert, and it was like 120 degrees outside. And I spent all day on the ground plane made of metal. So, it's a real treat. In 2018, EDGES actually was the first instrument to have shown the evidence of detection of the 21 centimeter signal. So that was a pretty big deal. It was a Nature paper. But turns out that signal was 3 times deeper and twice as wide than expected. So for those observant audience here, I'd like to point out that on the y-axis, you can see that that number is 0.6 Kelvin, which is 600 millikelvin, 4 times bigger than 150 millikelvin that we showed. But what does that look like if we were to plot it against any simulated expected signal that, based on the theory models that we had at the time? This is what it looks like. It does not help, it does not fit any of the models that we had at the time. So naturally, the entire community was quite divided. Some people got excited about the exotic physics that it can hold and how little we know about the early universe, right? So there's speculations, there's theories all around it. Could this be dark matter? That is, is there excess dark matter in the early universe that's absorbing all that heat coming from the stars and galaxies and making it look cooler than making the dip look cooler than we expected, right? Could this be excess radio background? Meaning, was the early universe brighter overall than we expect? And some of these are consistent with the current JWST observations, but we don't know for sure. We don't know confidently. Or could this simply be instrument systematics? Bad modeling, subpar electronics, bad thermal monitoring of our receiver electronics that can manifest itself to look like signal. So to be able to confidently answer that question, we need independent detections from various different instruments across the world. So we need one measurement from the northern hemisphere, one from the southern hemisphere, things like that, right? So one such example is an experiment called Saras, and this is the Indian counterpart that is after the same signal. And you can see that this telescope is actually deployed on a lake. The reason why they deploy it on a lake is to sort of get rid of those undulations that I talked about, because they expect the lake to be fairly flat, and you can model the electrical properties of the water a lot better than the electrical properties of the soil, because that affects how the antenna interacts with the moisture in the soil and the conductivity of the soil, etc. Water is a lot more manageable in your simulation softwares. But turns out that for them, the structures in the lake bed was also a problem. So you can think of how precise of a knowledge that we need to have to be able to make this confident measurement. But they did publish a result that basically rejected the edge signal by about 95% confidence. Fun fact, I actually did intern with them when I was an undergrad, so but the interesting thing here is that their frequency ranges were not quite the same. Their modeling analysis was not quite the same. So it's still kind of an unanswered question of whether or not the signal is real. So the tension of this detection is yet to be determined. And within Edges itself, we've had a lot of upgrades since 2018. We've had software upgrades. Astronomers are generally not good software engineers, but we have to learn to write software. But we now have a modular, fully retraceable, open source Python pipeline. The code that was used to publish the 2018 result was like 3 C scripts, exactly 3 files. And we also have new hardware. We have the capability of doing in situ calibration, meaning we can calibrate our instrument at different temperature conditions. And this especially helps us because the temperature fluctuations in the Australian deserts is a lot. So, to having calibration in the summer, winter, fall, etc., is a good practice. We also have a bigger ground plane. It's, like I mentioned, it's 50 by 50. The 2018 one was, I believe, it was 30 by 30. So the focus of my research is actually, analyzing this analyzing this newer data set that's much, much more sensitive than the data that was used in the 2018 analysis. So we call this the Edges 3 instrument, the new and improved. This was deployed in November of 2022. There is a total of 6 different calibration measurements, 225 different antenna S11 measurements, and essentially 2.5 years of continuous sky data. And you might raise your eyebrows when I said N10S11 because I did not introduce what that is. Let's just say that those 6 calibrations and 225 are the ones that are used to figure out if the data coming in is a signal or a smudge. So on the right, I'm showing the plot of the overall data, like a bird's eye view of what that data looks like. The top plot is the calibration measurements, and all the vertical blue lines are the days when it rained. And remember, rain means it changes the conductivity of the soil, meaning we can't trust the data coming in. And then the third plot from the top is the deviation from the set temperature. We need to be able to maintain our receiver at a very stable temperature, and it gets pretty hot in the summer, and we fail quite badly to maintain that temperature. And you can see that variation goes up to about 5 to 6 degrees Celsius in the summer, which is not good because we're trying to detect something that's in millikelvin, right? One of the other things that we do is we change our set temperature to 35 Celsius in the summer and 30 Celsius in the winter. But even with that, you see these big variations. So the second plot there is a set temperature. So we have a suboptimal thermal control. And what that manifests itself in the data is the bottom plot there in the green. In both commissioning and testing phase, you can see that the data is quite, it's all over the place. It's not stable at all. And to be able to detect the signal, one night of data is not enough. We actually integrate years of data together into one signal. So you can think of like a very, very long exposure. And so to do long exposure, you need very flat, stable conditions, right? And so we end up throwing out a lot of data. So we apply a very, very rigorous data selection process. One of them, like I mentioned, is rainy days. So we actually conservatively throw out any data the day before the rain, the day of the rain, and the day after the rain. We only select stable measurement. And we do that because now you might ask, oh, are you biasing yourself by throwing out data that you don't like? Like, how do you determine what you don't like, right? So we know roughly that the sky signal is fairly stable. It is global sky average, right? Like we are averaging the entire sky. We're not looking at one particular direction. We're taking the full sky measurement, and we know that it's fairly stable. If there's daily variations, it is most likely because someone turned on a radio, or someone turned on, like left a microwave open, or like somebody, or there's like people are doing maintenance work, or someone drove by very fast near or with their car radio on, something like that. Or if it rained, or the sun was very bright that day, the sun was quite active. And so that's why we throw out those days of data. In addition, we also, do data cuts where we only select the data where the sun is 20 degrees below the horizon. And that makes sure, and the reason why we do that is sun actually affects how the ionosphere changes its properties. And so conservatively, we just don't even use the data when the sun is 20 degrees or up. And we do the same with moon. We apply a 5-degree filter, meaning moon has to be at least 5 degrees below the horizon. The reason for that is any sort of RFI from the Earth gets reflected from the moon back to us. So we're that sensitive, right? So that's why we want to throw out that data as well. And then finally, we apply something called the local sidereal time filter, meaning we only use the data when the galaxy is not in our field of view. If you go and talk to a lot of astronomers, they get excited about galaxies and the science that you can do with the Milky Way. But for us, that's noise. We don't want it. It's like a million times brighter than everything else, than the signal that we are looking for. So we specifically take that out. And so we are left with, even though we had 2.5 years of data, we are now left with about, this is how much we are left with in the bottom plot. This is roughly about 180 hours of data. So you can think of how much data we just throw out. This is just one such thing that we do in order to make sure that we have good data quality. But in addition, we also have choices that we need to make for calibration. So think about the temperature at which the cable has to be, the length of the cable that we have, or the actual calibration of the cable itself, and the data reduction choices, like I mentioned, and the modeling choices for the actual signal extraction from the noise-like data. So each of these choices can affect the final signal significantly, some more than others. And so the key here is to make these choices agnostic to the final result. And the way we do that is by using simulated data set and testing a whole bunch of choices and seeing a choice that we can accept through a Bayesian-informed choice. This is another example of what the data looks like after all of the calibration has been done. After we are ready, like this is basically the data that is ready to be integrated into a single signal. So this is all daily after all of the filters that we applied and calibration that we did. That is the daily data from every selected day that we have. And obviously you can see that some, maybe it's hard to see, but some days have about 6 hours of data selected, some days have about 0.5 hours of data selected. But the results from this are out to be soon. So we'll see if the follow-up of edges still sees that signal that we originally saw in 2018. Another thing that we can do is ionospheric studies because of how sensitive it is. These are the example of solar flares, and you can see because of how sensitive it is, our instrument is, it completely, washes everything out in our instrument. But that means I can take a day off and go hunt auroras. So I'm not complaining. Okay, let's go back and now look at some of the other observational challenges. We have screen back there. Okay, it's back. But let's try and solve another problem here, which is incomplete sky map. So if we were to look at incomplete sky map, so this is the plug for my current postdoc work. This is the project that I'm working on with the Green Bank telescope. And we have custom electronics and antenna attachments. That picture in the middle is about 10 feet tall. And that actually goes upside down like that on top of the prime focus of the telescope itself. And we aim to make the map of the sky at a resolution of about 1 degree. Green Bank actually is it is the largest fully steerable telescope. It's also the largest movable structure in the world. So for reference, that's the Washington Monument right next to Green Bank. So you can see how large that is. It is extremely sensitive. You can detect a cell phone signal from Mars using Green Bank. That's how large it is. Like the diameter is about 320, I believe, 320 feet, or about 110 meters. And but you might ask, how is it so big and yet so sensitive, right? It's not a single, structure. It is made up of a lot of metal plates. So the way we make this extremely sensitive is by having about 2,200 actuators that ever so slightly move up and down and make sure that the overall surface is as smooth as a human hair. And we also have about 8 trucks that pull the entire telescope around and across. So the telescope can go both in azimuth and elevation like that. So we hope to use the sensitivity of this telescope with our custom electronics and custom antenna fittings to be able to make that sky map. So in the next 2 to 3 years, expect a new and updated map of the radio sky at these degree scale resolution. Now, I would like to introduce you to another problem that people didn't have to think about maybe 10, 15, 20 years ago, but we do now. So there's a lot of radio leakage from the communication satellites. I can't tell you which one, but we can see the evidence of that in the observations of LOFAR, low frequency array in the Netherlands. And you can see on the right the kind of noisy structure that it adds to our data, and that becomes a problem, a huge problem for us to do low frequency radio science. So where does that take us? To the moon. This is the far side of the moon, a picture of the far side of the moon taken by Artemis 2 crew on their recent Artemis 2 mission in April. Far side of the moon is unique because it is the most radio quiet region from the inner solar system, within the inner solar system. A little flex here. I actually met the person who took this picture not that long ago. But the project that I'm most excited about in the recent or in the near future is called LuSEE-Night. LuSEE-Night is a lander and a rover system. It's a Pathfinder mission. It's funded by both DOE and NASA. It's a CLIPS mission that is set to launch in 2027. And LuSEE-Night is going to give us some of the very first look of the radio sky below 50 megahertz. Below 50 megahertz. I said that the signal that we are after is between 50 to 200 megahertz. Below 50 meaning more Doppler shift, meaning we can look at the sky before cosmic dawn. And we call this the age of dark, we call this dark ages. So this is a very unique opportunity to look at what the universe looked like before the formation of stars and galaxies. Moon is also good for us because it doesn't have the same ionospheric effects as we do on Earth, and hopefully less RFI. And though that's also changing rapidly with growing interest in Moon now. This is another ambitious future project. So this is called the Lunar Crater Radio Telescope. So the lander is going to land in the middle of a crater. This is basically an Arecibo on Moon. It's going to land in the middle of a crater and it's going to shoot up these anchors to the edge of the craters, and the beam, which is essentially what collects all the signal coming in from the telescope, hoists itself off. There it is. It's going up. And the entire telescope, wait for it, it's going to open itself in origami style. Isn't that cool? This is currently under development at Jet Propulsion Laboratory in Pasadena. I think they have some initial seed funding for this. But this is a future ambitious project, basically doing a Arecibo on Moon. And you can see that satellite up there that helps us do the calibration of the telescope. Another ambitious project is called the Lunar Far View. It is a project of about 100,000 antennas on the far side of the Moon. And for reference, we don't have 100,000 antennas deployed on Earth. So think about doing that on Moon. And so there's a lot of cool, ambitious ideas around doing lunar science. So I'm going to play another one of these videos. Hopefully this one takes a lot less effort.
Exploring the pre-stellar dark ages requires approximately 100,000 10-meter antennas across 200 square kilometers. Transporting more than 60 tons of metallic antennas from Earth would be prohibitively expensive. Manufacturing metals on the Moon drastically reduces transported mass and overall cost. The coiled wire is used by rovers to deploy 10-meter crossed dipole antennas and preamplifiers. The rovers continue to build antennas until they complete an antenna cluster. "576 antennas form one cluster roughly the size of 20 football fields. 174 clusters create the full 200 square kilometer Far-View Observatory. Silicon extracted from regolith enables solar cell fabrication. The Moon's ultra-high vacuum allows thin film deposition without vacuum chambers. Regolith is melted into glass substrates, and layers of silicon and aluminum form thin film solar cells. Large deployed areas provide sufficient power for Far-View and future lunar systems. Solar cell arrays are installed at the center of each antenna cluster to power operations. Far-View only launches the tools needed to build the observatory. Far-View's in situ resource utilization approach will change how we operate on the Moon. Far-View will open the science horizons of our universe, and in doing so, will advance the technological development of lunar infrastructure that will advance the utilization of the Moon for the future of humanity.
Yep. So we hope to do that one day. You might ask me, why? Why are you doing all this, right? Okay. So then for that, I'm going to come back to this slide as to why there's this, there's missing pieces of puzzle in our understanding of the universe. And this is one of the really big ones, right? Like this is something that we hope to do in the next decade or so, hopefully. And so that's why a lot of us are in this game. We want to be able to, fill the gap, find more observational evidence, and hopefully whoever solves all those engineering problems, and hopefully anyone who solves all those problems revolving around finding very small signal in this very noisy environment, there's a Nobel Prize waiting there. The bottom line is that this measurement is extremely hard. We need to improve our systematics. We need better simulations. We need better sky maps. We need to be able to avoid radio frequency interference, and we need to improve how we handle our data and how we develop our analysis techniques. So there are many, many more opportunities in low frequency radio astronomy in the next decade and beyond. So if you're feeling inspired today, I'd like to give you this, a backyard radio astronomy project, which comes together using your Amazon boxes and aluminum foil and less than $100 of electronics. And you can detect this 21 centimeter signal, not from the cosmic dawn, but from our backyard Milky Way, okay? And so if this is of interest to you, reach out to me. I'm happy to share more resources. And finally, I'll leave you with this XKCD comic, because there's an XKCD for everything, right? And I'll take any questions. Don't be shy. Yeah. Do we have to pass the mic around?
I think you could just say it out loud.
Well, if you figure all this out, like, what knowledge does this unlock about the early universe or about physics?
Yeah, that's a really great question. So that dip that I showed earlier, that essentially tells us, if we were to figure out what frequency that dip happens at, you can figure out when were the first stars and galaxies started forming. And you can then figure out the age of the universe, the conditions of the universe, how quickly the stars were forming. Essentially, it lets us understand how and why the present day universe is the way it is.
You talked a lot about like calibration for soil and environment and circumstance. I know the moon is like in its atmosphere compared to us has a lot less conditions, but what would you need to actually be able to calibrate 34,000 football fields worth of?
Did people in the back get the question?
No, you repeat it.
Okay, the question is, what kind of calibration techniques do we need to be able to calibrate 100,000 antennas? There's multiple answers to that. One of them is an orbiting satellite. So that is going to emit a beacon of a known frequency, and so that is going to be like your basically your 0 point, your set point, and because then the satellite itself is going to emit something of known value, and you have to adjust for what that is. So that's one way. The second one is there's techniques that we use on terrestrial observatories called absolute calibration technique, wherein every telescope itself, like the one Edges that I worked on, the antenna box itself has something called like a full calibration system installed, meaning you do like a open, short, and load calibration of every cable that gets connected, right? And then the other thing that you can do is also the sky calibration itself. Like we can look at bright sources like Cassiopeia A, Cygnus A, Taurus A, things like that. So you would look at known bright sources in the sky and figure out how much does your telescope measure relative to the known value from Earth. There's multiple different ways of doing it. Overall, you can also kind of do this divide and conquer, wherein you select like one cluster gets calibrated together, and then you cross calibrate with the neighboring cluster, things like that. Okay, I'm going to repeat the question. What got me interested in this? I think big picture, in terms of like why I am doing cosmology is because when I was a kid, my grandpa would like sit us down and tell us how big and vast the universe is, and that kind of really got excited. It got me excited, and so I think in the middle of undergrad is kind of when I started looking for internship, and I got into a research internship. And the advisor that I started working on, he did some of this 21 centimeter cosmology. And when I understood what the problem was, I thought it was a very, very cool project to be part of and very, very cool science question to be answering. And so I kind of kept going, and I met my PhD advisor and did my PhD in the same science. Yeah.
Do you ever feel frustrated or impatient by how long these projects take?
Okay. The question is, do I ever feel frustrated by how long these projects take? Is that right? Okay. Yes. I guess yes and no. Yes, because this is something that people started thinking about. I mean, radio astronomy is relatively new. The first ever radio detection happened in the 50s. So we are like less than 100 years old as an electromagnetic radio, like, you know, within the electromagnetic spectrum. And I think in less than 100 years, we have come a long way. The prime example is the fact that all of us have phones in our hand, right? Like that's all radio communication, or at least the techniques that we use there, antennas and whatnot. But in terms of like this particular project, the theory came out maybe like 30 years ago, and the experiments sort of maybe 30, 35 years ago. The experiments started popping up maybe I would say like early 2000s. EGIS is one of the earliest ones. In fact, it's been observing since 2007, and that's why it's EGIS 3 now, you know, third generation. But I think there's a lot of instrumental and engineering problems that need to be solved. So really the bottleneck right now is those engineering challenges. And even though that I do have an engineering background, I feel very underqualified to solve any of these engineering problems. I think the science gets me excited more. And I think that's true for a lot of other astronomers, and that's why there's like this sort of mismatch of science and engineering within cosmology. Yeah. I'm gonna go first in a minute.
How do you go about securing funding for this project?
Uh-oh. I'm not going to repeat that question. It is very difficult now. I'm not going to lie, right? But EGIS is funded by National Science Foundation, though we have fully exhausted all of our funding as of, I would say, like this month. So it is frustrating to not have funding, and I think that's one of the problems that you know we are still trying to solve as a community in radio astronomy. People are coming up with like newer, you know, creative ideas. Like for example, lunar radio science. NASA and other private companies are extremely comfortable funding the Pathfinder missions. They're comfortable funding the, you know, like technology demonstration projects, but not for the actual payload. So they'll fund us to go to the moon, to build a rover, but not to actually put an antenna on it. And so that's kind of where we need to sort of start thinking about creative ways of looking at maybe philanthropy funding, or, you know, hopefully, obviously, like the best case scenario would be to increase federal funding for science cases, right? So yeah, I mean, it is unarguably one of the most difficult times in science this decade, and hopefully things get better, but we don't know.
In your opinion, what's the second most believable theory on the origin of the universe aside from the Big Bang theory?
The question is, what is the second most believable theory for the origin of the universe apart from Big Bang? That's a great question. I do not feel qualified to answer that question because I am an experimentalist. Sorry. Yeah.
If you got $1 billion to fund something, what project would you fund?
Oh, wow. Obviously, this is a near and dear project for me. So I think I would spend a good amount of money trying to figure out the systematics in our measurement. One of them is arguably to build the better calibration systems than what we have today. And then the second one would be to make the sky map. We do have some funding to do the sky map, which is why I have a job, thank goodness. But I think we need more kind of going back to like that engineering side of it, it really is to try and solve a lot of these engineering problems. And I think if we do that, we will have good data.
Actually, adding on to your engineering question, all these like development take across like multiple decades. Like, do you feel like if you start redesigning it now with the current state of engineering, like, do you think you could have like jumped that research up a lot?
The question is, it takes a lot of time to do engineering development. If we were to start now with the current technology that we have, would we be able to jumpstart it? Yes and no again, because a lot of technology that you see, I think this is something that I've been learning after I moved here to the Bay Area. There's a lot of like technological development that go hand in hand in both private and academia. But a lot of technology that gets developed in academia is already cutting edge. I think the real problem is that nobody has been able to solve, like, on a daily, scalable technological level. You don't really care about something that is of the order of 10 to the negative 6. You know what I mean? Like, there's the order of 6 magnitude difference in sensitivity that the private industry or technology development does not take into consideration that we need for science. I hope that answers your question. Yeah. I think there was one here.
Yeah, so that temperature dip that's like off by factor 4, what like underlying theories or principles that drove that simulation do you think are off that caused that major difference?
Let me get this right. So what?
So the simulations that showed that were off by factor 4 in that temperature dip, like, do you know what?
Oh, from what was detected versus what we expected at the time?
Exactly. So what you're expecting, the model was always like quite off. You know what kind of principles to expect were, or the theories behind that were off that could have accounted for that?
Right. There are actually, it's because it came out in 2018. Since then, there's been multiple different theories. Some of them sort of explore this exotic dark matter particles. Some of them explore excess radio brightness in the early universe. I think those are the 2 big ones, and then you can kind of, it can get more involved once you kind of, those are 2 big categories, I would say. Yeah.
How many people globally, like across all these different sites, would you say are working on this 21 centimeter problem? And how does it work?
How many people across the entire sciences, or just astrophysics or cosmology?
Well, like I guess you showed like I think several sites. So I guess I wonder, like, is this kind of like a smaller community, or is this like tens of thousands of people?
No, it's very small. It's actually really small. It's not even like 100. So the biggest one that, like, I guess the biggest number that I can tell you is people who do 21 centimeter cosmology. We organize a workshop. I'm part of the organizing committee. It's called the Global 21 Centimeter Workshop, and it's been happening for the last, I would say, like maybe 7 or 8 years. Because that's kind of like, it started in 2018 after the AGIS results came out, and then there was this need for, like, okay, we need to talk to each other, right? Like, all these people, we need to talk to each other. And so that conference usually has about 50 people.
So if there's only 100 people working on this, do you basically know everybody who's working on this?
Pretty much. I mean, sometimes it's hard to know, like, if, like a new student joins in or whatever, but like, it's, people talk, like, it's a very small community. Yeah.
How much of the engineering work you guys are doing to solve some of these challenges is bespoke, or sort of you guys are originating these solutions, versus borrowed from other disciplines or industries? And do you see much of an opportunity to do more of the latter than the former, particularly in light of budgetary challenges?
Did people in the back? Okay. The question is, how much of the technology that we develop is unique to the experiment versus something that's borrowed from other fields of engineering, to summarize, right? Almost all of it is unique to what we do. We do take some tools. For example, we have something called the Vector Network Analyzer, which is just a tool that lets us calibrate and receive the signal coming in from the telescope, right? Obviously, we use tools and such, Like for example, the software used to simulate your antennas in the cell phone, it's called a FICO simulation. Those and HFSS simulation, those are developed by companies like ANSYS. So we use the antenna simulation software, but we more often than not run into like the edge cases because they really don't think about our use case. I have colleagues who constantly talk to people at ANSYS trying to figure out, oh, this is this edge case and the solver can't help, right? But in terms of the actual hardware development, I would say even there, it's quite unique to what we do. Like one of the things that one of the engineers in our lab helped do last year was to take a receiver that's the size of maybe like this big and this tall into a miniature size so it can go to space, and it was all done in our lab. Yeah.
I think so. One of the biggest physics questions today is the unification of the theory of relativity with quantum mechanics. I was wondering if your research contributes to that, or if you think that's maybe the second part that's still the most important question to answer in physics.
Okay, did people get the question? Okay. Again, going back to the point that I do mostly experimental and observational cosmology, I don't feel qualified to answer that question. But I will say that in terms of like the grand unification theory, people that generally talk about, this is not something that comes up in our daily conversation, if that helps. Yeah.
What current bottleneck you have you think is most likely to be solved through AI?
Oh wow, I love that question. What are the bottlenecks that we hope to solve with AI? Certainly, we can do a better job at coding. At least that's what I use AI for, thanks to my husband, who's a software engineer. But other than that, I think in terms of like some of the optimization problems would be cool to see if AI can solve it better. Like for example, one of the things that I showed is the vast, analysis choices that we need to do, like that one. This is a very long list of parameters that we have to select, and each of these parameters, like my PhD thesis was 3 or 4 choices in that, right? So it is quite an exhaustive list that needs like months, if not years of work. And I think AI could potentially run a lot of these simulations parallelly and kind of make that make the analysis go faster. Yeah.
So do you need computational resources to run this analysis?
That's a good question. Yes and no. The exact experiment that I work on, it is unique in the sense that it integrates the entire sky coming into a single signal. So it is not data intensive at all. But if you were to kind of do a 3D mapping of what the universe looked like earlier, including the 3D simulation that I showed, those are computationally intensive. And the data that we collect from interferometers, for example, something like that involves 100,000 antennas, that is extremely data heavy. Yeah, that.
So this is like a logistical question, but you mentioned like the Milky Way, for example, is very radio bright, and there are like other celestial bodies that are also radio bright, like pulsars and stuff. Do you have to account for those when you're making measurements?
Yeah, that's a really good question. The question is, Milky Way is quite bright, but what about pulsars? Pulsars are unique in the sense that they're kind of time variant. So we are not that worried, at least when we're integrating the whole sky. But we do, I think there was a paper that came out maybe 2 or 3 years ago that took into consideration all of the point sources that we expect within a certain magnitude of brightness. And I think if I remember it right, it added about 1% of, overall, it added to 1% of the RMS in the noise level. Yeah.
I think you mentioned that the software pipeline you use is open source.
Mm-hmm.
So is that something that you guys built, or is that something that the open source community contributes a lot to?
It was me and 2 other people.
Oh.
Yeah.
Are there things that you want, open source community to help you with?
That is a good question. I don't know. I'll have to think about that. Because I think the use case is so unique that one of the things that we are trying to do is get other experiments to use our pipeline, because then that way we kind of can do like this cross verification of each other's data, and because every instrument is unique in its own way, even that becomes a problem. But that's a good question. I'll think about this. Yeah.
Piggybacking off that, you mentioned comparing each other's data with all the different sites. Is looking at measurements at the same time helpful at all? Or?
Not really, because this is a signal that comes from the early universe, and so we don't expect it to change on a daily or yearly basis. We actually integrate over an entire year. So you can confidently, compare the data from, let's say, 2035 to like 2015.
Remember, you're cross-calibrating the different sites and all their...
Yeah, even then it doesn't matter, because you can take the measurement of the temperature and all of the other things that are specific to the instrument, and you calibrate all of that out. So ideally, you're only comparing the signal coming from the sky, and that's time invariant.
Well, thank you so much, Dr. Vydula. Give her a round of applause. All right, that was amazing. If you don't mind pulling up that last slide. So, huge shout out to the Madroni Art Bar one more time for having us today. Please feel free to grab a drink and still support them while you're still here. So as you see up here on our screens, take a minute to scan this QR code if you haven't before. You'll find 3 links to it. The first is our upcoming lectures. So if you enjoyed tonight and you were so moved and you want to come out with more, check out the rest of this month's lineup. Second is our mailing list. So we do drop our lectures here or there the first of every month. Our events do sell out pretty quickly, so we strongly recommend joining to give yourself the best chance to grab a spot as early as you can. And third, our speaker application. So if you or someone you know would love to give a Big Brain lecture, we'd love to hear from you. So yeah, feel free to give it a scan, and then we wanted to give a little bit of a little token of appreciation from your loved ones, some flowers for you. So let's give one more big round of applause to Dr. Vydula. Thank you guys again, and have a good rest of your night.